Hi, my name is Anastassios Nanos. I'm the director of Nubificus, and I'm going to present Drop, which is a Type 2 project for the second open call of Nephele. In this presentation, we're going to go through the components of Drop, how it glues in with Nephele, and we're going to present 3 demos that describe and showcase the merits of Drop and how it enhances Nephele. First, let's go. Let me introduce who we are. We're a young SME. We're working on facilitating and optimizing application execution in cloud and edge environments. Our focus is mainly on system software. We do research and commercial projects. Our team has a diverse expertise of low-level system software ranging up to the higher levels of the stack, up to container runtimes, and we blend that, providing system software solutions for cloud-native ecosystems. Drop is essentially a project that facilitates the resource management of highly heterogeneous devices such as IoT, far edge devices into cloud-native ecosystems. Essentially, we've got 2 key features. The first one is that we are able to securely onboard IoT devices, either Linux-based or microcontrollers, and we're able to provide over-the-air updates for these devices, whether it's firmware or just a Docker image. And the second feature of Drop is that it provides the ability to offload heavy computations from these low-end far-edge devices to neighboring nodes that have the compute capacity to execute these workflows. The components of Drop are essentially the agent that handles the secure onboarding and offboarding, the agent that handles the over-the-air firmware updates, and the framework that handles the compute offload. This is a figure of the high-level architecture of Nephele and how Drop glues into the Nephele ecosystem. Essentially, Drop is a software framework that we install on an edge cluster. It is fully compatible with the Kubernetes API, and it interacts with the Nephele SMO, providing monitoring information about applications, about components of hyper-distributed applications that are running on this cluster and on IoT devices. And it also interacts with the VO management to be able to respawn or change what the IoT devices do. If we dig in a bit to the Drop architecture, we can see that there are 3 layers: the device layer, which holds all the far edge devices, the IoT devices, the Linux-based devices that are external to the cluster. We've got the edge cluster, essentially the node and the control plane. And we've got the cloud layer, which hosts helper services such as our attestation server in a secure enclave. What we built, Drop, is based on popular open source projects like Kubernetes, KTS, Acri, CSF Sandbox project, and our own components like the attestation server, the Flash controller, and the protocol that we talk to IoT devices, either Linux-based or microcontroller-based. This is the workflow for the onboarding and offboarding of devices. Essentially, an operator populates the secure enclave with a legit certificate from a device that we want to onboard on our cluster. There's the discovery handler of Acri, enhanced with our code to be able to do this attestation. And there's the leaf device that we want to onboard on cluster. So the leaf device upon boot generates a certificate based on a unique device secret. For simulation purposes, we have used the MAC address of the device, but this is based on what the hardware supports. It establishes a connection with the discovery handler, and it sends a unique certificate to the discovery handler. The discovery handler relays that to the attestation server, and if it matches the actual certificate provided by the vendor of the device, then it can safely onboard the device and the device can be used in the cluster. Otherwise, if there is no certificate or if the certificate is invalid, then the device is not onboarded. Let's see this process in action. So we've got a generic Kubernetes cluster. This is the edge cluster. In the Nephele terms, we've got 3 nodes, 2 VMs and the bare metal node holding a GPU. The GPU will be used on demos. And let's see the pods that are deployed on the cluster. So we've got the Acri installation, an Acri agent on each of the nodes. We've got an Acri controller. We've got the attestation server. And what we need to do is deploy the discovery handler. So let's go ahead and have a look at the discovery handler. So we say that we need application types vanilla. This is a secure discovery handler, so we need to do attestation. And it's an HTTP discovery handler, so we will check IPs from 1160 to 1170. The discovery handler itself is a container image. We provide the tag, name, and we can safely deploy the discovery handler. See, the container is being created, and we can get logs from this container to understand what's going on. As we can see from the logs, it has discovered the device. And if we inspect the Acri instances, which is essentially the devices, we can see that the device is being onboarded. Now, we can get more information about this device, and we can see its host endpoint, its version, its UID, and all that stuff. Now, this device was onboarded because we have already populated the attestation server with the legit certificate of this device. We can see that by listing all the available keys in the attestation server. So this is the MAC address of the device. We can also query the device ourselves. It's a vanilla device, a Linux device, a version 0024. All of this is done in a pure cloud native way. So if we would like to revoke the trust on this device because something happened and we don't trust it anymore, all we need to do is delete that from the secure ledger, delete the unique device secret from the secure ledger. So if we see what's going on now, we will see in the logs of the discovery handler that now this device is unauthorized. And we can see that there is no Acri instance now. The device was offboarded. So if we do, again, get Acri instances, we get none. And this will continue to take place until we re-inject the unique device secret in the attestation server. So if we do that, the device will be discovered again correctly, and it will appear again as an Acri device. So we can manage it through Kubernetes. Let's move on to the slides. So a bit of information about the flash job controller. This This is the part where we are able to repurpose a device by providing new firmware, either a Docker container or a firmware blob that will be flashed on the microcontroller. The controller, the flash job controller is a generic Kubernetes controller that gets a custom resource, a flash job resource. It spawns a pod, and this pod holds all the information needed to update and repurpose a Leaf device. This is the workflow for the Leaf device. So for the update of the Leaf device, so we create a custom resource. The controller detects that, creates a flash job. It queries Acri for information about the device. It creates the flash job. It establishes the flash job pod, establishes the connection with the device, and the negotiation for the OTA update takes place. And then, of course, we clean up. If we would like to see that in action, we can see the device. This is the device, so we can see that there is no container running. We can get the Acri instances. It's a single device. We will populate the flash job custom resource with our information. So we define a name, we define the UID of the device, and we have a simple version entry and a Docker container image. If we apply this flash job, this CR, we get a flash job pod. So if we get the logs of this pod, we can see that everything is successful. And if we go to the device, we can see that 7 seconds ago, this container is being deployed. This is the exact same container that we specified in the flash job custom resource. Of course, we can repurpose this device with another container image if we want. Could be a Redis example. Let's just change the version so safe that we know which version we run. And if we poll for the container, we see that in a couple of seconds, the device was updated. Let's move on to the presentation. Of course, everything is OCI compatible, and it's, since we are in a cloud-native ecosystem, for the Docker containers, this is just a string, so we pass the Docker container. The device pulls the container because it's a Linux-based device. However, when we talk about microcontrollers that they cannot pull OCI artifacts, what we've done is that we have packaged all the firmware blobs specific to an application per device type into an OCI manifest. So we've got ESP32 device, ESP32S2, S3, C6, whatever, and we annotate the container image, which just contains the firmware blob, a couple of hundreds of kilobytes. We annotate it with the platform name, ESP32S2 or ESP32S3. And when the flash job pod wakes up, it checks for the device type and it only fetches the container image containing this specific firmware blob. Of course, this process is automated and we are able to build applications, firmware blobs, in an automated way using GitHub Actions. Moving on to the offloading part of Drop. So internally, we've built a framework, we call it VXL. It's an API remoting framework that enables workloads to enjoy hardware acceleration without having direct access to hardware accelerators. Essentially, it's an API remoting framework, and it glues API operations to plugins that hold hardware-specific implementations of these API operations. It's highly interoperable. It has an optimized transport layer, so we have custom RPC plugins that enables users to run applications remotely. And of course, this flexibility enables users to use any hardware acceleration framework, the TensorFlow, PyTorch, TVM, whatever, or custom ones for NPU. This is the high-level architecture of VXL, and a generic application consumes the VXL API, for instance, an image classification operation or a TensorFlow model load, model run operation. And these operations are, through the VXL library, matched to hardware-specific implementations of these operations for these plugins. So we've got a CPU plugin that implements image classify, a GPU plugin that implements TensorFlow model run, an FPGA plugin that could implement pose estimation, for instance. So all this mix and matching is done at runtime. And of course, there's a remote plugin, an RPC plugin, that you are able to, the application is able to call image classify as it would, select the specific plugin, and specify a remote address where another VXL application, the VXL agent, is running, again with the same stack, and it consumes the same API, only now the remote VXL instance has a hardware-specific plugin specified. Let's see that in action. So we've got an example, we've got a BERT torch hate speech classification example. What it does, it receives text and it says whether this is offensive language, hate speech, or neutral. And this is a stock torch operation with a generic torch model. We run it and we get some numbers. We port it to VXL, and now using the generic torch API that we have in VXL, we're able to run this application over the network. So from a node to a remote node by specifying its RPC endpoint. And the remote node can have a CPU implementation and a GPU implementation. Let's have a look how this works. So on the same cluster that we have already deployed the VXL agents. So we've got on the cloud node, let's say, we've got a CPU agent and the GPU agent. And we have the client application, the BERT classifier, on a Helm chart. And we also have prepared a Grafana dashboard that shows the CPU utilization of the cloud node, the CPU utilization of the VM node, of the worker node of the cluster, where we will deploy the client application, the GPU utilization of the cloud node, and the inference rate per second and inference latency in milliseconds per tweet. The input dataset is a set of tweets that contain various offensive language, texts, hate speech, and neutral. This is the panel that the data will start coming once we deploy the application. So let's do a Helm install. We have a couple of options. So we set the variant to stock. This is the stock application, no VXL involved. We will deploy that on the specific node, and we will set the number of threads used for torch to 1. So this will trigger the VXL client creation, and if we go to the Grafana dashboard, numbers start coming, and we can see CPU utilization in the node that we deployed the application. Since it's stock, it starts saturating one core because we used one CPU thread. The inference latency stabilizes around 60 milliseconds, so 63, 64, and the inference rate is around 15. The CPU utilization of the cloud node is the same as before. It doesn't affect it since it's not related to this experiment. this test. Now, if we want to update the client application and we would like to use VXL, so the only thing that we need to specify is remove the variant, the stock variant. So without the stock variant, it will run VXL, and set the remote endpoint where the application where the RPC plugin will point. So we will use the CPU agent for now. We'll deploy the application again. We can see that the VXL client, a new VXL client container is being created. And let's have a look at the numbers. We can see that the CPU utilization of the cloud node is increasing because it runs Torch. We will slowly see that the CPU utilization of the VM node will drop because it doesn't use the CPU for Torch. It uses the CPU just for the remote execution. So remote requests receiving responses. The inference latency remains almost the same because there is a balance between the remote overhead, the network overhead, and the fact that the cloud node has more cores than the VM node. However, the inference rate remains low. And if now we go and change the endpoint and use the GPU reaccelerated, we will slowly see that we will have GPU utilization. The inference latency does a peak because it's a Torch thing, but it will drop immediately. We will see lower CPU utilization on the cloud node and on the because CPU is not involved in the heavy computation. It's just for the plumbing, the issue requests, receive responses. As we can see, the inference latency per tweet drops and it stabilizes around 11. We can see that the rate per second is something more than 55, almost 60, compared to 15 that was earlier. So we can see the clear benefit of using such an approach in a pure cloud native way, running a simple application that is compute intensive on a really low end VM, and offloading this computation to a neighboring node that holds a GPU. Let's go back to the slides. Drop was implemented in 6 months. So in the first stage, we set up the requirements using the implementation and integration plan provided by the mentors, and we defined the technical KPIs. In stage 2, we did the actual implementation. We enhanced the VXL transport layer and we tailored it to be able to run Torch better. Also, we implemented the Cloud Native IoT project. This is the internal name, Drop. And we did the integration with the Nephele ecosystem. On stage 3, we did the evaluation of what we implemented in stage 2, both for the mechanisms and the end-to-end evaluation. Drop aligns perfectly with Nephele goals. Essentially, it enhances the Nephele's SMO with real-time IoT device integration, both for orchestration, for workload orchestration, and for efficient execution. The technical KPIs that we defined were all achieved. For instance, for the VXL case, we also have an example with YOLO, where we run an object detection model in Torch, and we achieve 10x frames per second compared to running it on a Raspberry Pi on an edge node. The same for latency. We've got a 10x improvement in latency reduction. And of course, offboarding and onboarding times are look really good. So we can onboard a device provided we have the certificate in 13 seconds, and we can offboard the device in 22 seconds. Thanks very much for listening. We were really happy to implement this project and to integrate with Nephele. Everything is open source. You can find the code in our own repos on GitHub or on Nephele's GitLab. There's a specific folder named Drop under OpenCall 2. It was a really fun project for us. Thanks to the mentors for the help with the integration and for onboarding us into Nephele. Feel free to reach out to us if you have any questions. Feel free to check out the code, the documentation. There is plenty of documentation to walk you through and get you started with Drop. Thanks very much for listening.